Good morning, everybody. Different format today because we're having difficulty with GoToMeeting. It's been going on now nearly 24 hours, and so this is going to be on YouTube. I'm filming on an iPad, on a really old iPad, right now, and so I'm going to put this up on YouTube. I don't know if you'll see the light of day of it, but I couldn't just stop because of GoToMeeting. IT's working on it, I hope. I don't have a microphone. And there's no transcripts. But what we're talking about here, this is section 2.5, and it's unfortunate that the format of the video is different right now because this is a really theoretical section. I'll talk about that. It's really theoretical. But here's the agenda, the epsilon delta method of proving things, and then the formal definition of a limit. An example, problem-solving strategies, another example. And then I don't know whether we'll get to these or I'll make another video. I hope by that time GoToMeeting will be reinstalled. The homework for this section, it's section 2.5, is on page 206. There's only 3 problems. Number 177, number 188, and 189. And this is a tough section. Again, it's highly theoretical. In every single calculus class, in the history of calculus, right now is the next week, actually, or so. The first two sections of chapter 3 are theoretical. We're using the limit definition to determine derivatives. So hang in, okay, because it's highly theoretical, and I would really recommend that you get a different perspective than just here, particularly when we're on YouTube. I would just type into a search engine, formal definition of, we call it precise, a formal definition of limit. And they'll have all these pictures. I'm going to draw you a picture, but you can move them. That's actually an applet in this chapter. You can move epsilon and delta so I would just recommend for this particular section, in order to really, really enhance your understanding, find a different perspective. With that said, this is theoretical, and the next 2 or 3 sections are going to be like this, but once we get past there, calculus moves pretty quickly. Okay, so that's where we are. Hey, you folks made comments on the videos. I've got a few of you had comments, and I really, really appreciate that. To a person, you all said, oh, well, we're shorter than... I made one that was 25 minutes long. At one point, I thought, I can't put a 25-minute video up. So then I started doing 2 or 3 particular. So I appreciate that. So here we go. We're into 3 minutes. I haven't done anything yet. So the precise definition of a limit. We're headed towards this thing. We have a curve. We're headed towards this thing. We want the slope of the tangent to a curve. And in order to do that, we went through limits because, there was a secant. We moved that point closer to that point. And so that's where we're headed. That's chapter 3. It's called the derivative. But in order to get there, we do this thing with limits. And in order to do that, we need a precise, a formal, I put formal there, I'll use precise, definition of limits. Definition. Of limits. We need a formal definition of limits. And in mathematics, there's a branch. After you finish with calculus, you would take a class called analysis. Real number analysis, actually. And in real analysis, everything is proven. You just can't make a statement without proving it. And in order to do that, we use things called epsilon delta proofs. There we go. Epsilon delta proofs. I make my epsilon like that. It's actually, I should do it like that. I don't know why, but I think all my life I've been making epsilon like that. It's hard to change. Delta, those are Greek letters, of course. And so we're proving things. And so epsilon delta, let's do this. Let's write the formal definition. Formal definition of a limit. And then we'll talk quite a bit more about epsilon and delta. Which one? If f of x is defined, f of x is defined at x, but x doesn't equal some number a, then the limit of f at x as x approaches a is L, if and only if for every epsilon, well, I'm going to tear this sentence apart over this board again. For every epsilon greater than 0, there exists a delta greater than 0 such that, aha, I told you I wanted the other board. For every epsilon greater than 0, there exists a delta greater than 0 such that. By the way, when you take analysis, nearly every day you'll be proving things using this. You start out every proof like that. Such that. Okay, so I'm going to write that a little differently. For every epsilon greater than 0, there exists a delta greater than 0 such that, I mean, as I say, you're going to do that so, in higher level mathematics, you're going to do this so often that that's how you write this sentence. Let's see, if 0 less than x minus a less than, if x minus a less than delta, then 0 less than f at x minus L is less than epsilon. That's the formal definition. That's the formal definition of a limit. And I just want to take this apart. For every, this is for every, meaning all, every, no matter what epsilon is, no matter epsilon, there is a delta. All right. Such that. And then this part right here, let's take that apart a little bit further. How about just saying x is within x is within delta of a. How do I have this written? If x is closer to delta, then f at x is closer. Yeah, let me just write what I just said. X is within delta of a, while f at x is within epsilon of L. I told it's theoretical. 8. Wow. Let's draw some pictures. Just draw a picture. That's the formal definition. And this is, it's the close to bit. I'm going to erase this because this is where I'm going to put the picture. And so, we have a function here. There's f at x. And we want, here's a. And we want to show that as x gets closer and closer to a from both sides, the function will get closer and closer to L. F at a equals L. I mean, that's intuition, but that's what we want to show. So here's how we do it. We want to get, there's a delta smaller and smaller and smaller. Like if you choose that delta, that corresponds to f. Here, I'll write this stuff up. This is L plus or minus epsilon. That's this distance is epsilon. This distance is a plus or minus a delta. And as this gets smaller, but the point always is, no matter how small, no matter how tiny this is, there will always be a delta greater than 0. And all we have to do is find a delta in terms of epsilon. Oh, boy. let's do one example, and I just have to see how this video is. You might not see the light of day. Prove just a linear limit, and I'll take it from the book. Prove the limit of 2x plus 1 equals 3 as x approaches 1, right? Prove that. I think that's what we have. 2x plus 1 equals 3. Okay, so we want to prove that. And intuitively, well, of course it does, bro. But so what we want to do is we want to assume, first, assume epsilon greater than 0, no matter what. 2, choose a delta in terms of epsilon. Now that's the hard part. In this case, we're choosing delta over epsilon over 2, and I'll show you why. Problem-solving strategy is 3. Just show that 0 less than x minus a less than delta. Show that. Then f of x minus L is less than epsilon. That's what you want to show. And then, then once you do this, it's proven. You're done. So we're going to do it with that problem right there, over here. 2x plus 1 equals 3, the limit as x approaches 1. Okay, so now just assume an epsilon. Now we want to choose a delta. 1, epsilon greater than 0. 2, choose a delta. All right, now here's where it gets interesting, because we want to be able to say x minus 1, that's the limit, is less than some kind of delta. So now we have to choose that in terms of epsilon. So if this is what we want to say, then please note 2 times x minus 1 is less than 2 delta. And then so this is 2x minus 2, and then we want to subtract 3 from it. That's 2 times x minus 1, and we're still there, is less than delta. And then so this is 2x minus 1 is less than delta, which is what we want. And so choose delta equal epsilon over 2. This is the hard part, right there. Then 4, x minus 1 less than delta, which by the way is epsilon over 2. Then, let's see, 2x minus 1 is less than epsilon. 2x minus 2, absolute value, is also less than epsilon. 2, 2x minus 2 minus 3 is also less than epsilon. Oh, plus 1, I'm sorry, that's right, that's what I did wrong the last time. 2x plus 1 minus 3. Then it's proven. We chose a delta. And so you could just say, this is less than epsilon, because this is true, then that's true, proof. Okay, that wasn't so good. I don't know if you'll see this. 14 minutes, bye.